Welcome all. In this presentation, we will talk about spoken dialogue system, but focus on a specific domain, which is the belief tracking. And for this, we will be discussing two papers, the neural belief tracker and SUMBT based model. So these are the kinds of the recent advances in this domain. So we will first begin with our secondary paper, which is our neural belief tracker, followed by SUMBT model paper. And then we'll have a short summary followed by a Q&A session. So a spoken dialogue system, as we all know, they enable a human to computer interaction, and the prime agent is human speech. But as we all know, the human dialogue is much more complex than that. There are lots of things like going on. And as a user, I would be more interested in having a flowing and engaging conversation, like throwing arguments, reasoning, etc. But the certain rule-based dialogue system don't allow these, where you have only a particular predefined set of outputs for a specific input. So the moral of the story is that the robustness is a big challenge, and the NBT and the SUMBT based models solve these issues by making the conversation as natural as possible. So this is a typical block diagram of a spoken dialogue system that is designed for only a specific domain, that is a restaurant domain. And it begins with using an automatic speech recognition system to transcribe the speech into a stream of text. And in order to make meaning out of this text, we have an SLU component. That generates information and meaning from the generated text. Then we have a DST, or dialogue state tracking module, which is known also as a belief tracking module, which maintains the different states of the dialogue. So as to say, if I'm a user and I ask for a restaurant, so the DST must understand that the goal of the user is a restaurant search. Hence, the type becomes a restaurant. The dialogue management component plays a managerial role, where it uses some knowledge base, which is kind of an ontology comprising of a range of user intents. A simple understanding, So what you see here to your right is an example of a ontology. So given the restaurant domain, and in order to inform the user of a potential restaurant, the system must know of the food category, that is either Asian or Italian, by looking at the ontology. And it then outputs dialogue actions, which are passed to the NLG module to obtain a natural response, which is then used by the TDS to generate a speech. And our talk will be focused on the dialogue state tracking here. So this was something, a task oriented. We also have some statistical based approaches, where statistical approaches like a Markov decision process are used to perform dialogue state tracking. It maintains some kind of distribution for each of the possible slot and value pairs, and the one that yields maximum reward is chosen as the best slot value pair. So the traditional approaches like the discriminative or a generative or a rule-based system suffer from lexical variability, where you have differences in the choice of words, where the system looks for a matching slot value pair in your ontology as interpreted in the user utterance. They also so these are the problems that the traditional approaches suffer from, and you also need a large manually constructed semantic dictionary to identify possible slot and value pair that is being mentioned in the user utterance. And if an utterance has some word that is not found in the dictionary, then yeah, your system just fails miserably. These problem limit the scalability and kind of a capability of the dialogue system. Hence we hence the need for a more robust system like neural belief tracker. So the neural belief tracker, it was first proposed in 2017, and it aims to leverage the deep learning, the modern deep learning approaches to perform dialogistic tracking. And so its goal is to detect a slot value pair in a dialogue flow where it takes 3 inputs. The last system, the current utterance of the user, the current utterance of the user, then you have the most recent output that led to that user utterance, yeah, and a slot value pair. So a slot value pair we will see is being abbreviated as we pair, and think of it like in terms of a variable name and a variable value. For example, if I say please go ahead, so your slot will be the variable name, which is the direction. So we are talking about the direction here. And since and this variable name can accept will have a value which is the goal is to move forward, so the value will be forward. So once it takes these inputs, it iterates over all possible slot value pairs and decides which one best expresses the user goal, and we'll see in further slides how this is done. Yeah, so we have these 3 components, and the learned context representation and the utterance representation are combined together to form context modeling. Further, the utterance representation and the candidate representation, they are interacted together to perform semantic decoding, and some interaction summary is obtained. We also have a gating mechanism, which performs kind of a sanity check, where only those utterances are passed that are concerned with the current slot value pair. So, all in all, we have a three-way interaction to that leads to a final decision. So in this paper, the model uses pre-trained vectors to encode to encode word into vectors. To encode word into vector that expresses the similarity, that expresses the semantic similarity. So in this illustration, all possible n-gram or all possible unigram, bigram, and trigrams are accumulated to form an n-gram representation, and then they are further mapped using some nonlinear representation like sigmoid, and they are summed in an unweighted manner that represent the final user reference. And a similar variant of this prototype is implemented using CNN, where instead of these cumulative n-gram representation, we have convolution filters for each of the n-gram. And this is better suited for long-range utterances. Next, we have semantic decoding, which checks whether the current user utterance indeed matches the current slot value pair. And this module uses two models to perform decoding, which is delexicalization-based models and semantic dictionary. So these are the kind of baseline models. And in the lexicalization-based model, the slots and values mentioned are rather replaced with a generic label. For example, if I talk about looking for an expensive restaurant, so here the generic label will be, so I'm talking about food, so the generic label will be the food, and it's involving some about prices, so the generic label will be price range. Next, we have context modeling, where the goal is to have a belief tracker with a clear understanding of the context. This is done by modeling the most recent system utterance, and based on the last user utterance, the dialogue can form, like two acts. It can form system request, or it can do a system confirm. So in a system request, the system requests the user information for a specific slot. Yeah. So for example, if I talk about what area would you like to try, the user must answer the question to this slot, like area slot, the value to this slot. So he wants to go to downtown. And if in case of a system confirm, the system asks the user to confirm the slot value pair using some positive or negative response. And then the binary decision maker compares each of the slot value and finds the best slot value pair, and finds the best one that is being represented. So this work uses a kind of a rule-based approach to update the belief state, where in each dialogue turn, the model estimates this probability of slot and value pair given a list of ASR hypotheses along with the preceding system output, in order to have a combined estimate for the entire dialogue. The model performs a turn level estimation, and these are all cumulated to form the cumulative belief state for the entire dialogue. And this is indeed a linear combination of the first dialogue turn plus 1 minus lambda of all the remaining dialogue turns. So here we have lambda. It's like a kind of a fixed hyperparameter that determines the weighing factor for each of the dialogue turn. So this work uses DST2 dataset and WOS 2.0 dataset, with each having around 3,000 and 1,200 total number of dialogues. And these are like the single domain restaurant domain data set with each having only three slots like food area and price. So the performance of the proposed model for our main paper and the secondary paper as well will be the joint goal accuracy of the request accuracy. So the joint goal accuracy is a measure of a fraction of dialogues where the user's goal with the goal expressed by the user, it is slot and value pair were correctly identified. While in a request accuracy, the measure of a fraction of dialogue where the information requested by the user were correctly identified. Now we'll see the results. So we have baseline models and proposed models. So baseline model. So we have two baseline models. One is a delexicalization based model and a combination of delexicalization along with the semantic dictionary. So what's a semantic dictionary? So think of it so think of it in terms of ontology, where it has all possible rephrasing for slot values. And if you see carefully, we have we have a pretty much better performance of the proposed model than the baseline models. However, in both joint goal accuracy and request accuracy. However, this difference is not very prominent or significant if you see the DST data set. This is mainly because DST data set is not so rich in vocabulary and is filled with ASR errors. So the credit to increased performance accuracy goes to the specialized word vectors that play an important role in handling semantic variation to produce a high quality intermediate representation. Those word vectors I'm talking about. So the most important takeaway from this paper, is the capability to not rely on handcrafted dictionaries to model dialogues using deep learning approaches. However, certain shortcomings still haunt us, like failure of this approach on multiple domains. As we saw, both of these data sets were only for a single domain with only 3 slot values. 3 slots. Hence, a need for a more robust approach to perform scalable belief tracking that can handle multiple domains. And this is something which is taken care by the SUMBT-based models.